In most developed regions, residential life is inseparable from centralized electricity infrastructure. Lighting, refrigeration, heating and cooling systems, communications, and domestic appliances are all designed around uninterrupted grid access. This dependency is not incidental. Over the past century, energy production shifted from localized mechanical generation to centralized utilities capable of serving entire cities from a limited number of power plants. Transmission networks expanded, substations multiplied, and regulatory frameworks formalized distribution. As a result, the modern household was built into the grid by design. Electrical panels, code requirements, appliance standards, and financing models all assume permanent grid connectivity. Mortgages, insurance policies, and building permits often reflect this assumption. Dependency in this context is structural rather than behavioral. Households periodically attempt to reduce their exposure to centralized systems.
Some focus on conservation, lowering thermostat settings, upgrading insulation, replacing appliances with higher efficiency models. Others install rooftop solar panels, battery storage units, or fuel-powered generators as contingency measures. In certain regions, time-of-use plans encourage shifting consumption to off-peak hours. In others, net metering arrangements allow limited energy exchange between homes and utilities. These approaches adjust the relationship between the household and the grid. However, in most cases, they do not remove the connection itself. The meter remains installed. The billing cycle continues. The infrastructure tie-in persists. The grid remains the primary reference point. The persistence of dependency is reinforced by several constraints. First, centralized grids benefit from scale. Large generation facilities distribute costs across millions of users, making per-unit pricing competitive in normal conditions. Replicating that scale at the household level introduces economic friction. Second, residential architecture is standardized for grid input. Most homes are wired for alternating current supplied at specific voltages. Full disconnection requires redesigning electrical distribution systems to ensure stability, safety, and compliance.
Third, regulatory frameworks often require inspection, permitting, and adherence to utility interconnection rules. In some jurisdictions, complete disconnection affects property classification, resale conditions, or insurance coverage. Finally, there is informational inertia. Understanding generation capacity, load balancing, storage requirements, and seasonal variability introduces technical considerations that most households are not structured to manage continuously. Together, these elements create continuity. Remaining connected is simpler than redesigning the system. Despite this continuity, alternative formats have existed historically. Early rural electrification often relied on localized mechanical systems, small turbines, engine-driven generators, or community-scale distribution networks. In isolated regions today, distributed systems still operate independently, combining mechanical motion, limited storage, and direct load applications. Modern technology has also enabled small-scale generation methods that do not rely exclusively on sunlight or fuel combustion. Some designs explore mechanical amplification principles, regenerative motion concepts, or hybrid low-friction assemblies to convert small inputs into usable electrical output. These formats do not replace national infrastructure at scale. They operate at a different scope, designed for limited, localized continuity rather than full industrial demand. They represent structural alternatives, not universal substitutes. Within this landscape, digital blueprints and instructional systems have emerged that document small-scale, self-contained energy assembly concepts. These materials outline how localized generation units can be constructed using commonly available components.
Such systems are presented not as replacements for national grids, but as structural supplements, frameworks designed to operate independently from centralized distribution when required. They exist within the broader category of distributed energy experimentation and documentation. Their role is defined by structure rather than promotion. They describe configurations that function outside traditional utility dependency. The evaluation and adoption of such formats remain individual decisions shaped by local regulations, technical considerations, and personal priorities. Grid dependency persists not because alternatives are inconceivable, but because centralized infrastructure integrates deeply with residential design, economic scaling, and regulatory continuity. Disconnection introduces structural friction. Connection maintains procedural simplicity. Most households remain on the grid because the surrounding systems, financial, architectural, administrative, and informational, are aligned around that model. Dependency, in this sense, is embedded. Understanding that structure clarifies why the default remains unchanged, even as discussions around autonomy, resilience, and distributed generation continue to evolve.